Computers are very powerful. We use them every day. We have one in the back of our pockets that we carry constantly, and we can't really imagine our lives without them. But what if computers could be even more powerful? Let's take weather forecast, for example. The computer takes weather data and simulates the way the atmosphere behaves based on the laws of physics, right? But we know that the weather forecast is only good for maybe 5 days, 10 days, but at this point it really starts to get very inaccurate. What if I told you that quantum computers can make accurate weather forecasts for months, maybe even years? Sounds crazy, right? Well, it is. So, what is a quantum computer? Or maybe we should start by asking, what is quantum? Quantum mechanics is a branch of physics that describes the behavior of matter and energy at the smallest scale, so atomic and subatomic levels. It's a completely different world than what we know from our day-to-day reality, and it behaves very differently. Just like the wizarding world of Harry Potter is a magical world that exists within our own world, but behaves very different from what us as non-magical people, muggles, know. So let's discuss one of the most bizarre features of quantum mechanics. Let's assume I have a coin here on the table and it's facing heads up. Now, the state of the coin is not going to change whether or not I'm observing it, right? I may not know what this state is without looking, but that's just an expression of my lack of knowledge. Now, in a regular computer, this coin is simulated through a bit, a 1 or a 0. In a quantum coin, the situation is a bit different. The quantum coin has a more fluid, non-binary identity. It can be both heads and tails at the same time. And it has a certain probability of being heads and a certain probability of being tails. Now, this time, the uncertainty is inherent to the state of the coin itself. It's not an expression of me not knowing what it is. And this weird combination of 0 and 1, or heads and tails, is called superposition. And it's one of the most fundamental, basic facts of quantum computing and quantum mechanics. Now, when I turn to observe this coin, this weird fluid coin, it suddenly becomes either heads or tails, immediately. And if it sounds really weird to you, then it's okay. And if you're very confused by quantum mechanics at this point, then don't worry, you're getting it. Okay. Now, so a quantum computer is a new type of device, but what can we actually do with it? And how is it different than a classical computer? So I would say that since our quantum coin can now be in a superposition of 1 and 0s, the rules of the game called computing are completely different. Okay? A quantum computer is not simply a more powerful classical computer, just like a light bulb is not a more powerful candle. We cannot build a light bulb by making better and better candles, right? A quantum computer is a new type of device based on a deep scientific understanding of quantum physics. So, what can we actually do with a quantum computer? Is there anything interesting we can do with it? And the answer is yes. There are many possible applications for things we can do with a quantum computer that we can't really do with classical computers, or at least not in reasonable time. And these are just a few examples. So we have, for example, drug design. We have cryptography. Cryptography is how we secure our information. For example, our credit card information. So it's very important. Weather analysis, as I described before, and molecular simulations. We now understand that our world is quantum. So it only makes sense to use a quantum device to simulate a quantum reality. But my interest in quantum computing is a little bit different. And it's probably not going to be the first result that's going to pop up on Google when you search what can a quantum computer do. And that is that the quest to build a functional quantum computer has allowed us, and me in particular, to take a fascinating detour into exploring the fundamentals of quantum mechanics. And ask questions about, for example, the delicate nature of measurement of quantum systems. And that is exactly what we do in our lab. So what do we do in our lab? Or to put it in other words, how does one build a quantum computer? So while classical computers are well understood and easily reproducible, the truth about quantum hardware is not very known. There are many different techniques that can be used to make a quantum computer. And one of the leading techniques, the leading architectures that is used by industry giants like Google and IBM and a modest small research lab like our own is superconducting qubits. So what are superconductors? Superconductors are materials that when cooled down to very, very low temperatures exhibit zero resistance, not small resistance, but zero resistance to electrical current. So in our lab, and we go to this beautiful clean room, and we take those materials, we take thin films of aluminum or niobium, and we deposit them on a substrate like silicone. And if it rings a bell, then that's because it's very similar to how classical transistors are made. So we make these tiny chips, and at the end of this process, which is called fabrication, we end up with something like this, which is basically a tiny, tiny circuit that behaves like an artificial atom, therefore exhibiting quantum properties, which is great. It's exactly what we want from a quantum bit, from a qubit. Then we take this quantum bit, this qubit, and we cool it down to very, very low temperatures to invoke the superconductivity. So what you see here is a picture of our lab, and the reason it's so clean and organized is because it was taken on day one. So it no longer looks like this, unfortunately, but this golden stuff right here is nothing but a very expensive, very fancy refrigerator. So we take our chips and we put them in the refrigerator, and after 48 hours, we have a quantum popsicle. And what can we do with that? So do you remember that coin I told you about that can be in a superposition of 0 and 1s? And I also told you that once you observe it, it immediately becomes one of the two options, either 0 or 1. Now, if it sounds really weird to you, then it's probably because we don't really know why it works. And it's called the measurement problem. When I say observe the coin, I mean measure the state of the coin, measure the qubit. And the measurement problem is one of the biggest open questions in quantum mechanics today. Now, I'm not saying I'm going to give an answer to this question, but by using the technology given to us by superconducting qubits, I can take this system, cool it down, perform various kinds of measurements on it, and maybe try to shed some light on the measurement problem. And so this is what I do in our lab. Now, I hope that by this point, I've managed to convince you that humanity can greatly benefit from having a working, full-scale quantum computer. And I also just show you that if you walk five minutes that way, you can go into our messy lab and find a working qubit. So why don't we have 5-year weather forecasts? Why don't we have all those cool things I've mentioned? Well, the reason is that while there have been some very impressive breakthroughs in recent years, there are still many, many challenges that need to be overcome before we have a fully functional, realizable quantum computer. And one of them is the problem of noise and error correction. So quantum systems are inherently very, very fragile and can be easily disrupted by environmental noise. That's why we also need to cool them down and protect them. And that of course, can cause errors in computations, and we don't want that. And when I say errors, I want you to think about your phone. It has billions of transistors in it. A transistor is the basic unit, the bit in our classical computers. And for just one such transistor to have a bit flip error, meaning that the 1 suddenly becomes a 0 without me wanting it, it takes a long time for this to happen. And by long, I mean tens of years. So it's very, very stable. A bit flip is not a very frequent event. But in a qubit, and specifically this one right here, our superconducting qubit, it happens much faster. It takes, for a bit flip to happen, it takes about 20 microseconds. You need to take that in, because it's really fast. A microsecond is 1/1,000,000th of a second. So if this error occurs so fast, I can't even fix it, right? So what we do in our lab, one of the projects we're working on, is making the quantum hardware better on the 1-qubit level. So to make them perform better, then we can start thinking about scalability. So in order for us to be able to do all these cool calculations I was telling you about, we have to have large-scale devices. And by large, I mean millions of qubits. And currently, the largest working quantum computer today has around 400 qubits. So we're nowhere near that stage. And this presents a major technical issue, because in order to overcome this, we would have to come up with new fabrication techniques, new materials, and new control systems that we just don't have currently. And overall, while there is much work to do in the field, I would say that the progress that has been made in recent years is very, very impressive. And the potential applications of quantum computing are vast. And if I have to put it in weather terms, I would say that the future of quantum computing is bright and sunny. Thanks, everyone. Also, I just